Hello friends, welcome to Truth of Physics. Today in this video I will discuss and calculate the wave function of an infinite symmetric potential wave. Okay. Now what is that? Suppose we have a symmetric potential wave or infinite 1D box. Okay, but symmetric. That means here the origin is here. This is minus a by 2. This is a plus a by 2. This is a 1D box or symmetric potential well, where outside this wall, this is infinitely long. Okay, this is infinitely long. Outside this well the potential is infinity, and inside it the potential is 0. Okay, now how to calculate that? We have to just first using the traditional thing, that is the Schrodinger's wave equation plus v psi. V inside we are talking only for region 1, this region 1, because we know that outside it the potential, as the potential is infinity, that means the wave function is always 0 outside it. Outside the wave function is equals to 0. So what will happen inside it? So this is 0 plus v psi equals to e psi, where v is equals to 0 inside. What will happen? So d2 psi over dx square will be equals to k square psi, where k square is equals to minus 2me, or not, sorry, plus h cut square. This is our k square. K is the wave number. So what will be psi? Psi is equals to a e to the power, or we can write it a e to the power ikx plus b e to the power minus ikx, but we'll not do that. We'll write it in the sine and cosine form. So how you can determine that when you have to use the e to the power ikx, this type of terms, and when you have used a cos kx, because these two things are equivalent, but you can see in books that in some cases they have used this form, in some cases they have used this form. So whenever there is no boundary, okay, then you can use this form, and whenever there is a sharp boundary, this is a sharp boundary, minus a by 2 and plus a by 2, so then you can use this form. Okay, so this is just something to say about these things. Okay, now what will be this? So here there is a sharp boundary, that means we can use a cos kx plus b sine of kx. Now from here it is very easy. Now what will happen? We know that this symmetric potential well, the potential, this potential is even potential. That means v of minus x equals to v of x. You can easily understand that. Here v is, here you can see that this is symmetric, right? This is the origin, and the potentials, the value of the potential is just symmetric. Here it is 0, so for that you can think that how it is becoming an even. But if you think of a harmonic oscillator potential, that is like this. So from here you can easily understand this is 0 point. So this potential is symmetric, right? If this is suppose x point, this is x point, so the value of the potential, right, the value of the potential here is suppose v1, that will be simply, or that will be just equals to the value of the potential at minus x. That means that is same, right? Because this potential is symmetric, so the value of this potential here, this potential here and here is just equal. That means v of minus x is equals to v of x, and here the similar thing is happening. So this potential is a symmetric potential. Infinite square potential is a symmetric potential. Now as the potential here is a symmetric one, so the Hamiltonian, corresponding Hamiltonian, which is nothing but about kinetic energy plus potential energy, right? Now kinetic energy is always symmetric, right? We know that kinetic energy is always symmetric, but and potential here is also symmetric, so the total Hamiltonian is also a symmetric here, right? As the Hamiltonian is symmetric, so the commutation of the Hamiltonian with the parity operator is 0. That means Hamiltonian or the even operator, actually the even operator, Hamiltonian here is the even operator. So the even operator commute with the parity operator always. So here Hamiltonian will commute with the parity operator. That means whenever the two operator commutes, that means the two can have an joint eigenstate, or the two can have can be expressed with the same eigenstate or eigenbasis, you can say. And we know that the eigenstates of a parity operator, the eigenstate of a parity operator is always, will always have a definite parity. The eigenstate of a parity operator always have definite parity. So as a consequence, the Hamiltonian, the eigenstate corresponding to the Hamiltonian will also have a definite parity, right? Because these two have same eigenstate here, right? These two have same eigenstate due to the Hamiltonian is commuting with this parity operator, and parity operator have definite parity. The uh, eigenstate of parity operator have definite parity. That means the Hamiltonian have also a definite parity eigenstate. That means the eigenstate psi we find here, that means this psi will always have a definite parity. Definite parity means what? Definite parity means it can either be even parity or it can be odd parity. It cannot be between even and odd parity. What is between even and odd parity? Suppose the psi is in the form of sin x. Then if we put minus x in place of x, that means you will get psi is equals to minus psi. That means this is a odd, right? This is a odd function. That means this is odd parity. Similarly, if we put psi is equals to cos x, you can easily check that this is a even parity. But what to say about this thing? This is a combination of sine and cos. So if you put a psi of minus x, you will get what? A cos kx minus b sin kx, which you cannot write in terms of psi anymore, psi of x anymore. That means this wave function is not an even or an odd. That means this wave function have not a definite parity. So this wave function cannot be a wave function of this symmetric potential well. Now, how to find the proper wave function for the symmetric potential wave? Now, let us recall the case of the asymmetric potential wave. I have discussed it in a particular video. The link of the video I will get in the description box. The asymmetric potential wave. Okay. Now, what is the asymmetric potential wave? That looks like this. This is the asymmetric, right? Potential wave. This was 0, this was A. This was our asymmetric potential well, this, okay. Now this is just, so our current symmetric potential well, is just a shifted version of the asymmetric one, right? So the wave function, we can think that the wave function will be just a shifted version, right? The wave function of our symmetric potential will just be a shifted version of the asymmetric one. And in our asymmetric one, the wave function was root over 2 by a sine n pi x over a. So in the symmetric one, in our present case, the symmetric one, its wave function will be what? Psi will be equals to root over 2 over a, because the length is same. This is a again. So root over 2 over a sine, okay, root over 2 over a sine n pi by a into, in bracket, x plus a by 2, because the origin is shifted, minus a by 2. So the wave function will be x plus a by 2, this thing, right? So what we will get? So from here you can easily understand that depending on the values of n, right, whenever n is odd, that means 1, 3, 5, 7, this type of things, this will look like this: root over 2 by a cos of n pi x over a, right? Whenever the n is odd, you can understand that this will be this, and whenever the n is even, okay, this is for n equals to 1, 3, 5, this type of things, and for n equals to 2, 4, 6, this type of things, what happens? This will take sine n pi x over a. So these two things, this this is the wave function of a symmetric potential wave. Whenever, that means the first excited state or the ground state of a symmetric potential will be what? The ground state means n equals to 1 here, that means odd, that means root over 2 by a pi x over a, right? This is psi ground state. For first excited state, what will be that? First excited state, root over 2 over a, n equals to 2, that means sine will happen, sine 2 pi x over a, and corresponding the and the energy will be same, right? The energy will be just same, E equals to n square pi square a square square over 2m l square, just same as our asymmetric potential wave, right? So this is all about today's video. I hope that you have understood that how the form of the wave function for the symmetric potential wave comes. Okay, so share this video with your friends, and if you really benefit from this video, then subscribe this channel and hit the bell icon. So take care of yourself. Thanks for watching.